All right, so this description of the two samples was brought up and used in our general discussion about comparing two population proportions. And so now we are ready to push forward and make this description here become an actual problem so that we can see directly the steps and further details of how we can compare the two population proportions. And so now I'm going to formally set out the first question regarding the description of the two samples we're having here. And this first question here is becoming our first problem. And we can use this as one example in continuation with the general discussion lecture that I delivered earlier. And so now, after looking at the description of the two samples here, now the question is asking at alpha equals 0.01. So recall for yourself this style of wording it, alpha equals 0.01. So alpha has, throughout this course here, has been understood as the significance level. So at alpha equals 0.01 are the samples showing strong evidence that there are less female drivers who favor a manual transmission. So there are less female drivers who favor a manual transmission. And the question itself are the samples, these two samples showing strong evidence. And so apparently, in a way how the question is worded, this problem brings us into the testing a hypothesis problem. So less female drivers who favor a manual transmission, but less female drivers, think a little further, less female drivers, less than what? Less than the male drivers. So basically this question right here, there are less female drivers who favor a manual transmission, means that after we have defined our lowercase letter p to be the proportion of drivers in general who favor driving a manual transmission, and also that we have discussed and decided that male drivers population is assigned the numerical label 1, and on the other hand, female drivers population is assigned with the numerical label 2. And so now in that way, there are less female drivers who favor a manual transmission. What I was in the middle of saying earlier is that now it means we are trying to prove that P2, this is proportion of female drivers who favor driving a manual transmission. We want to prove that P2 is less than P1. So P1 here is the proportion of drivers in the male drivers population who favor a manual transmission. And so now this is the comparison statements that we are testing, and it's the comparison statements about the two population proportions, P2 and P1. So this comparison statement here came straight out from the wording of our question that we have seen on the back on the computer screen, and it's an inequality. But now the idea is as follows. We will not directly test on a comparison statement like this, but instead we take a preliminary step as following. Algebraically, P1 less than P2 is equivalent to saying that P2 minus P1 is less than 0. That's one way to algebraically and logically re-express this inequality statement. And this way of how we algebraically re-express the statement here turn the inequality as another inequality where we're comparing a difference with 0. And alternatively, this same comparison statements we can also algebraically re-express that as P1 minus P2, but greater than 0. So we have, at this point, my bottom line here is that I have two different ways to re-express the same starting comparison statements here algebraically into these two inequality statements. And so now, in connection with what we did earlier, I have discussed in the general discussion lecture that there's a quantity that's the quantity dp is defined as p1 minus p2. So in that way, with this definition, which stays permanent, and regardless of whoever is playing in the role of p1 and in the role of p2, in that way that we have defined dp to be p1 minus p2, then let's have a look at this expression here. Even though, as I said earlier, we have two equivalent algebraic re-expression of this statement, but now we realize that p1 minus p2 greater than 0, this difference in this current inequality statements is consistent with our definition of dp. So we recognize that p1 minus p2 here is actually the dp, whereas here it's the opposite way around. And so I am now going to choose this specific statement right here to be regarded as the statements that I'm going to be directly testing with. So again, simply it is because the difference on the left hand side here is consistent with our definition of dp value. Alright, so from what it said right there, then since we specifically chose to work and test on this statement, and let's one more time rewrite that statement here, p1 minus p2 greater than 0. Now I want to see this statement as dp is greater than 0. And then further looking at this statement here that arrived at dp greater than 0, we recognize now that we have a statement that involves an inequality. So in that way, back to our first responsibility to identify the two hypotheses. Anytime we're doing a testing hypothesis problem, then this statement that we have just now recognized can be used in place of our alternative hypothesis. So now our alternative hypothesis H1 is saying that dp is greater than 0, and this is the hypothesis that we're proving right here. And so now in that same experience we have done for testing hypothesis on any value before, then no hypothesis this time can be recognized as dp equal 0. And so consequently, in that way, this problem, this testing hypothesis we're about to do in the same experience how we have learned through testing hypothesis, is then when our alternative hypothesis has an inequality that points to the right hand side, the test we are about to perform is referred to as the right tail test. And so before I proceed any further, I have to make clear the one thing right here. If we now look back to the wording of the problem, the wording actually started out saying there are less females. We want to prove that there are less female drivers. So less than male drivers, of course, but there are less female drivers who favor a manual transmission. But now again, surprisingly, when it came to our H1, we actually turned that into a right tail test. And so what I need to be clear here is that anytime we're testing a hypothesis, comparing two population values, and specifically here we're comparing two population proportions, then just because the wording in the question saying less than doesn't mean that the alternative hypothesis has to be less than in here. It all depends on how we assign the numerical labels for our two populations. So it's simply because right from the beginning, right from start, when I was going over the general description, I set for that decision that I assign numerical label number 1 for the male drivers population, and And in that way, numerical label for the number 2 for the female driver's population. And that's how it resulted in our alternative hypothesis becoming the right tail test. So this exact same problem could have also been, and I repeat, this exact same problem could have also been a left tail test if the numerical labels for the two populations here were given the other way around from the beginning. So now, as a bottom line, getting a comparison problem into a right tail test or getting the same problem into a left tail test is entirely dependent on how we have assigned the numerical labels for our populations. And so anyone who is about to do a problem comparing the two population values, either population proportion values or population mean values, we just need to be ready as a skill, as essential skills of how to be able to run right tail and left tail tests so that we can be ready for any case that can happen. So it's not only because the wording here say less than that would make the problem become a left tail. Obviously, in this problem, it was a right tail because it was all depending on our decision for the numerical labeling in the beginning. And so now, upon successfully nailing down our two hypotheses here and deciding that our test here is a right tail test, or to run our test here as a right tail test, then we are now ready for getting into the formal steps of getting our test done right here. Our test where we test our two hypotheses here. So the next step I'm about to show here, or formally the first step in testing these two hypotheses, I would like to introduce for anyone learning from the lesson here the following calculation. So there will be a lot of new values that I'm bringing in, and eventually I will give all the explanations to any of these values that I'm introducing. But first, we're going to look at a formula that calculates as following. We're going to need a p hat c value multiplied with 1 minus p hat c. And this product here will be further multiplied with 1 over n1 plus the fraction 1 over n2. So notice of how I went through my order of operation here, and these two are two separate fractions, 1 over n1 and 1 over n2. I agree that I have not at this point explained where that p hat c came from, and the explanation for where this p hat c came from will come out shortly. But then after finishing this product right here, we're going to put the product in a square root. So the formula here is the square root of all that calculation. So whichever the value that come out after this calculation here, we regard to that as the approximate. The purpose of doing this calculation here is to come up with the approximate for a value I call sigma dp hat. So again, the calculation that we proceed here in the next step, the final answer to that, the final calculated answer to this is used as the approximate for a value, another value that I call sigma subscript dp hat, or for short I'll just call that the sigma dp hat. And in the later steps, I will be able to explain what exactly the sigma dp hat is. And so looking at the entire formula here for now, anyone viewing the video here is looking for an explanation to what p hat c is. Okay, so let's now look back at the earlier part where I list down all of the sampling information. Alright, so now let's spend some time to find out how we can calculate p hat c right here. So p hat c, as I said earlier, the subscript c right here means combined. So this p hat is a sample proportion. So allow me to use a name. We can think of this as a combined sample proportion. It's a combined sample proportion. And so here's how we're calculating it. For our specific problem right here, for our specific problem where we had the two samples given here, then p hat 1 was at sample size 450. And p hat 2, even though not required to be the same sample size, but p hat 2 was also at the sample size for 450. And so this is how I'm calculating my p hat c right here. My p hat c, the denominator of my p hat c is the total of the two sample sizes. So 450 from p hat 1 plus with 450 from p hat 2, and I put that as my total sample size, and that's why it's called combined. We are combining the two samples together. So the two samples total up their sample sizes to come up with this overall larger sample size. And so in that way, once we mix everybody together, once we have mixed everybody together and poured the two samples, combined the two samples together, then of course their successive count, 170 and 170 from the male driver sample and 100 from the female driver sample will be also mixed together and total up. So here in the numerator of my p hat c, I'm having 170 plus 100. And that is, ladies and gentlemen, how I calculate the p hat c value. So generally speaking, I mentioned a little bit earlier that the value on top of each of these proportion here is called the successive count. And so successive count is x1 from population 1. And successive count for population 2 is called x2. So this is x1 and that is x2. So the way how the formula was set up, that I was doing it, x1 plus x2 divided by the total of n1 plus n2. And this is how we set up p hat c in general. So normally how I approach the problem, I tend to lead my students or my viewers directly into getting it. And then when we're done, I'm going to restate the actual formula that ran behind the scene. And so this is the formula to calculate the combined sample proportion. So now back to this particular problem, our p hat c in this case is 270 over 900. Final calculation gave me a 0.3. So this is not p hat 1, neither p hat 2, but this is the combined p hat. The p hat that we obtained by totaling up the two samples and also totaling up the successive counts in the two samples and put them all together as a combined, as a pooled sample proportion. That's what the 0.3 is. And so now we are ready for nailing down the actual calculation for this approximate of the sigma dp hat value, because we have now, after you have seen the explanation, then we have now had a value for the p hat c value. So from the explanation we have seen just earlier, then p hat c now would be 0.3. So I'm substituting that into my formula. So 0.3, and everything is done currently inside the square root. So 0.3 times 1 minus 0.3. And I'm going to multiply this product with another expression right here. So now 1 over n1. This is sample size n1, as we have seen earlier already. So 1 over 450, as n1 is equal to 450. And we're going to add another fraction, 1 over n2, where n2 is also 450. So in this problem, it happens that we have two sample sizes to be equal. And now this overall product must be placed inside a square root. And again, this is the approximate. Succeeding with this calculation here will give us the approximates to that value where I call the sigma dp hat. And at this point, I still have not given out a formal explanation of what this exact sigma dp hat is for our work. So now, final calculation of this formula. So when we're typing in to the calculator, make sure to type it out carefully, and I recommend that we finish typing out all of this multiplication inside the square root first, and then whatever that comes out from this product right here, we're going to take a final square root, and you can see that throughout the way how I have been writing that. I wrote down the product inside and then take square root as the last one. And so final calculation came out being 0.0306. So on the calculator that I used, this value came out a lot longer. And so for this particular video lesson here, allowed me to round this to 4 decimal places. And so now again, this is understood as the approximate value, the approximate to that sigma dp hat value right there. But I still have not explained at this point what exactly the sigma dp hat value is doing for our work right there. And so when you're working on your own problem, make sure to watch out for rounding requirements for the approximate of sigma dp hats, because it might be different in every problem. So after calculating the approximate for sigma dp hats, now I'm going to advance over to looking at the value of our actual sample. So in this case, what we have here is a dp hat, the difference, the sampling difference between our two sample proportions. Now, for this particular lesson here, I am going a little bit off from the formal order of the steps. Normally, when you see me doing that, I will be nailing down or listing down the value for dp hat first, the sampling difference in the two sample proportions, before working on the sigma dp hat approximate. But in here, I violate the order a little bit, so that later on I can bring a better explanation. And so now, to see the value for this dp hat value right there, the sampling difference of the two sample proportions, let's swing back to the part where I listed down all of the sampling information. On this given information regarding the two samples, then we have had one sample from population 1 and one sample from population 2. And so in that way, now we can recall that we define dp hats to be the difference between a sample proportion from population 1 minus a sample proportion from population 2. And that's why right here from what we already have, we can find, and this is our dp hats that we have, we can find the difference between our two samples that we're currently having. So 0.3778, I'm subtracting 0.2222. So this is our dp hat value, and it's only one among infinitely many other dp hat values out there. So final calculation of mine came out for this dp hat value to be 0.1556. And so now back on this writing board of mine right here, dp hat can now be listed as 0.1556 as a positive value. And so this is now our sample value as a sampling difference between the two sample proportions. And so now, upon getting the value for dp hat as our sample here, I must remind anyone that the sample value we have here is not the only one sample. The sampling difference we have here is not the only sampling difference. There are infinitely many other sampling difference dp hat values out there. So now we are ready for an explanation of what that sigma dp hat is for us. We can think about this dp hat and infinitely many other dp hats can all be placed on a bell curve. So now I'm going to draw a bell curve. So any value on this line is a possible value that we can find for dp hat value, where ours here is 0.1556, but other may be different. And so any of those other values for dp hat can be found on this line right here on our bell curve. So that's a random variable, dp hat. The center of this bell curve is at 0, the value being stated in the null hypothesis here. And so this bell curve, just like any other bell curve, once we know that it's a bell curve, it will have an average spread, and that's what I call that. It's a sigma dp hat. So sigma dp hat truly is the average spread of this bell curve right here, representing all values of the dp hat, the sampling difference in any of our two sample proportions. However, calculating the true value for sigma dp hat is a very challenging work, which requires a lot of advanced understanding. And so for our class here at this level that we're learning, we only rely on this calculation here that we have done earlier as the approximate, and it works good enough that many generations of statisticians have been using it. So we use this calculation, which gave us this value here, 0.0306, as a close enough or a good enough approximate to sigma dp hat. And so sigma dp hat is the average spread on this bell curve, and it has this approximate value. So we can use this as the approximate for average spread on this bell curve, 0.0306. And so now in that way, we can see that our sample value right here, dp hat, is found as a positive 1.556, is found somewhere to the right hand side on this bell curve. And now let's take a quick pause to allow me to point out a couple checkpoints for consistency right here. So our dp hat value is calculated and listed here as a positive value. So as a checkpoint for consistency, we should check that the positive dp hat value, this sample value of ours being positive, should be consistent with the alternative hypothesis stating that our dp should be positive, greater than 0, and should also be, this dp hat value should also be consistent with the fact that our test, according to our labeling convention, was decided to be ran as a right tail test. So those are the two checkpoints for consistency that I would like to point out. And throughout the steps later, I should be able to point out some other checkpoints for consistency as well. And also I must emphasize again that it's all due to the beginning decision where I assigned label 1 for population, for male drivers population, and label 2 for female drivers population. And that was the reason why this dp hat was found as p hat 1 minus p hat 2. So again, just like that, we always want, for any difference, either the difference in the two actual population proportion values, or the difference between any two samples, we always want the value from population 1 minus that similar value but from population 2. And that's how earlier when we were doing this calculation of the dp hats, we ended up with consequently a positive value. And so now, upon realizing that our sample value as a dp hat here can be placed on a bell curve here, and this bell curve has an average spread that it can be approximated by this calculated value that we have calculated previously, then now for this sample value of ours, we can proceed to calculating its z-score. So z-score for our sample here, just like how we find a z-score for any other value on a bell curve, we're going to take the difference between this sample and the bell curve center. So 0.1556 minus 0. So that's the difference between the value and the bell curve center. So this value 0 right here came from the bell curve center, or the value 0 here is the value that's stated in our null hypothesis. The difference there is now divided by the average spread on this bell curve. So 0.0306 is placed in the denominator. Calculation came out for my z-score to be 5.08. and it is a positive z-score. So allow me to write the sign of our z-score here in red ink. The actual calculation of this z-score on the calculator came out a lot longer, but allow me in this lesson here to round this to 2 decimal places. And for anyone doing the work here, make sure you watch for your rounding requirements in how far to round for the z-score. But now that after we have had z-score successfully calculated, we can now start out our next step here by calculating the p-value for our sample. So now we know that our sample is on this bell curve. Calculating the p-value of this sample here is done by setting up the probability calculation, where we're looking for among infinitely many dp hat values, we will find one that's greater than or equal 0.1556. And so now let me point out a couple other checkpoints for consistency right here. So again, this z-score right here being positive should be consistent with the fact that our alternative hypothesis is stating that we want to prove dp being positive being greater than 0. This z-score being positive should also be consistent with the fact that we have concluded, we have decided to run our test as a right-tail test. And this z-score being positive should be consistent with the fact that we are now calculating our p-value using the right tail inequality in our probability calculation statement right here. Look at that inequality that I'm writing in red right here. It's stating greater than or equal to. So those are a few checkpoints that we can check for consistency. So calculating this probability on this bell curve is understood graphically as the area shaded to the right hand side of our sample value 0.1556 on this bell curve. And so the p-value here is understood graphically as how big that shaded area to the right hand side of our sample is. And so now, since we know the z-score for our sample, calculating this p-value or calculating this probability on the bell curve here is the same as calculating the probability value where we run into a z-score greater than or equal to 5.08 on the standard normal distribution bell curve. And so now to obtain this answer, to find this actual answer, it's just now a matter of running a technology, relying on a technology to find this answer for us. So on a TI 83 or 84 calculator, I'll be running the normal CDF command. In order to find that area or this amount of area here. So now on our calculator here, we're going to call our normal CDF command by pressing the key combination second variables, which will bring up all of the distribution functions in statistics. Normal CDF command is found under option number 2 right here on our calculator. And I'm going to hit enter. And what I have here is a menu after we call the normal CDF here, because the version of the TI-84 calculator I'm using here is the most recently released version of the calculator. For anyone using a TI-83 or some earlier release of the TI-84 calculators, after calling your normal CDF command, instead of seeing the menu as you have seen earlier, you will be seeing the command being printed on your home screen as seen here. And so now back to the calculator version that I'm using. Now we're about to enter the low end and the upper end for our interval, for our shaded interval. So one more time, looking back at the writing board here, the picture of the shaded area here has a definite low end at 0.1556, or equivalent to the z-score positive 5.08, and it has an indefinite upper end. So that means on my calculator here, for lower end, I'm going to enter positive 5.08. So just simply 5.08. And now I'm going to hit enter. The upper end, as we have seen on the picture earlier, is an indefinite upper end. So I'm going to enter 1E99 for my upper end. And I'm going to default mu and sigma to 0 and 1. And hit enter a few times. And so now some words for the TI-83 or earlier TI-84 users right here. So if you see your command of the normal CDF program being printed directly on your home screen, you are responsible to type in the lower end and the upper end into your command manually. So put lower end here right after the opening parentheses with a comma, and the upper end with a comma, and default mu and sigma to 0, 1. And then we ending the command with a closing parentheses. And now for all versions of the TI calculators, we are ready to hit one last enter to obtain our final answer. So now this is our final answer right here for that probability, the probability where we find a z-score greater than or equal 5.08. And so back on my writing board, allow me to spend a minute here to complete the command, the syntax here for this program. So normal CDF with open parentheses 5.08 as the lower end on the z-score, positive 1E99 as the upper end, and then we're going to put a comma, 0 and comma 1, and we'll close our command right there and ready to execute it. So the answer we have seen from the calculator was written as, according to the calculator, 1.890397.6 and a lot longer, but with the E minus 7. So this is just the way how the calculator is expressing it, but what it means here is we're having a value in scientific notation about 1.8903976 times 10 to the negative 7. So that's what it really means for us in scientific notation. And this is the E notation here, just the way how the calculator is indicating it. But this value in scientific notation really means our actual p-value is in the actual decimal value 0.0000006 zeros before 189.039 and a lot longer. And so now in this video lesson, I am going to round our final p-value to 4 decimal places. So this lengthy decimal right here is rounded to 0.0000. So this is our final p-value that's rounded to 4 decimal places. So for anyone working on this kind of problem, make sure you watch for the rounding requirements of the p-value of your final p-value. So now that we have found our final p-value, concluded as 0.0000, we will now need to compare this with the significance level given in the problem. And so now back to the computer screen where it was having that description of the two samples and brought up as an actual testing hypothesis problem. Then I highlighted this earlier, and now let's highlight that again. But the start of this question is asking at significance level 0.001. So right here, this piece of information that I was highlighting here tells us that we now have significance level given at 0.01. And direct comparison shows that our final p-value is well below the given significance level. And so upon realizing that our p-value as a direct comparison is well below the significance level, we are led to the conclusion that our sample as a dp hat is an unlikely sample. And being an unlikely sample leads us to a further conclusion that our sample as a dp hat is, we can say, showing strong evidence, or itself is strong evidence. The sample itself is strong evidence. All right, and the strong evidence here, on one hand, for us to reject H sub 0. Or we can say we have strong evidence for us to support H1, the alternative hypothesis. One more time into the wording of the problem. Are the samples showing strong evidence? So we were looking for having strong evidence or not, according to the way how it's worded here. And the question is a yes or no question for the answer. And ultimately, we showed that we had strong evidence. Our dp hat has been shown to have strong evidence. So in that way, I'm answering yes as the ultimate answer for this question. And now we are brought to question B of our current problem here. So right out from the same exact description of the two samples we've had and we've been working with throughout the lecture so far, then this particular question asks us to find a 99% confidence interval to estimate the difference dp. All right, so that's a couple highlights to catch regarding this question that we're about to do right here. And so right here in the wording and right from the highlighted information that I just pointed out here, then the question here is intended for us to calculate, to come up, to find a confidence interval. And so at this point, I have to mention that this video lesson, this general lecture that we are reviewing here, is highly recommended to be viewed after you have already had, and I'm talking about the viewers or my students, after you have already learned about how to find a confidence interval in general. And so assuming that viewers arriving at this video lesson have already learned about how to find a confidence interval, then I can quickly remind about the following understanding. For any confidence interval, mainly to find it, and again, CI is my shorthand writing for confidence interval. So for any confidence interval, to find it, we have to rely on a sample value. So we must find a sample value. And so a sample value here is a lot of time either given or purposely found by ourselves, the people who are working on the problem. So we must first have a sample value, and from where our obtained sample value is, we are going to add and subtract with the margin of error. And so again, this is the reason why I'm saying that this video lecture here is highly recommended to be viewed after you have learned about how to find a confidence interval, because all this concept here has been highlighted and specifically emphasized in the video lessons that introduced about the idea of finding a confidence interval. So here I can just remind that this E right here stands for, is the symbol for margin of error. That's why I'm writing that in red ink. And another highlight to remind, after you have viewed my other videos about to learn about how to find a confidence interval, is that confidence interval is always used to estimate a value. And so in our case here, let's look back at the wording in the problem right here. So now we want to estimate, we want to come up with the confidence interval to estimate the difference dp. And so this is the value that we want to estimate. And so dp we have already understood. as the definition that we have seen earlier in the beginning of this lecture, then dp is defined as the difference p1 minus p2. And this is the value now that we need to estimate. And so in that way, since we're estimating dp, then the corresponding sample value for dp is going to be our dp hat that we have already found. So now if we're looking back at our chart that we have sketched down earlier in the beginning of our lecture here, then P1 is the population proportion of male drivers who favor driving a manual transmission. And the similar here, P2 is that similar proportion, but in population 2, where I named that the female drivers population. And so we have already gave that, we have previously given that definition dp to equal P1 minus P2. And so this is the value that we want to estimate using the confidence interval. But then corresponding to this dp value that we're attempting to estimate, then the sample value that I'm talking about, the sample value that we will be using to construct our confidence interval is this dp hat value. So dp hat value is the sample value corresponding to the value, the main population value that we are trying to estimate for. And so in that way, according to the given information we have already had here particularly, we already have for ourselves a sample value, which is the dp hat that we're having right here with value 0.1556. And so in that way, our final interval must look as following. From where the sample we have obtained, the sample value we have obtained, we are going to figure out the margin of error and add and subtract that from our obtained sample value. So this is ultimately what the final confidence interval of ours will look like. And even further, since we have already had the value for this dp hat, so I know for sure that at the end, where we finally come up with our confidence interval, then it should be taking 0.1556 as a center point, as a middle point in our interval, and add and subtract a margin of error. So now this is the main goal that we're looking for. So it looks like in this way right here, then we're almost done with our confidence interval, except for we need to figure out how big, how large that margin of error must be, in this case, for our desired confidence interval. And so really at this point, what I owe anyone viewing this video is an actual formula to calculate the margin of error for estimating the difference in the two population proportions here. So margin of error for our confidence interval to estimate dp is given by the following formula. E equals the z sub c multiplied with a square root expression, where inside of that we're doing p hat 1 for whoever is in place of p hat 1 times 1 minus p hat 1 divided by sample size decided on population 1, so n1. And still inside of that expression, we're looking at adding with another quotient, p hat 2 multiplied with 1 minus p hat 2 and dividing that by n2. So this is our formula to calculate the margin of error that estimates the value dp. And so now for this current formula, then the bigger part of this formula already contained all of those values we already had. So we have already had and listed down p hat 1, and in decimal it's 0.3778. We also had p hat 2 and listed down it's 0.2222. We had sample size for population 1 being n1 equals 450. We had sample size for population 2 listed here as 450, n2 equals 450. So in that way, we can almost complete this formula to calculate our desired margin of error. So we still haven't gotten to the z sub c, so now I'm going to leave that there, but at least the bigger part that is inside the square root here, I am going to have 0.3778 for p hat 1 in product with 1 minus 0.3778 for p hat 1, and I'm dividing that product by the sample size n1, 450. And I'm going to need to extend this a little further. And then still inside the square root here, I'm going to substitute in my p hat 2 values, so 0.2222 in product with 1 minus 0.2222, and that is to be divided by the sample size n2. So this is the bigger part, and it's ready for some calculation. So really what we need to know now is how to calculate the z sub c. And again, I emphasized earlier that this video lesson, this general lecture about comparing two population proportions is highly recommended to be viewed after you have already learned about how to find the confidence interval. Because back in those earlier videos when you have watched about finding confidence interval, you have seen and you have had some understanding about what the z sub c is. And so specifically the lowercase letter c as a subscript here, it is, so this is a z-score relative, or the z-score corresponding to the given confidence level in our problem. So as a reminder, for this particular problem, our confidence level is given as, on the wording of the problem, we want to find a 99% confidence interval. So it's a confidence interval, but this percentage right here is indicating that we are looking at the confidence interval to be as highly successful as 99% confident. And so in that way, now I have a given, this is given information. I have a given confidence level being 99%. And so now, even though confidence levels a lot of time are expressed or given as a percentage like this in our problem, but when it actually gets into doing any real calculation with this confidence level, we will need to write it as a decimal. So I'm going to write this as a 0.99 in decimal for any calculation that later on uses this confidence level. So now let's find z sub c, and allow me to be a little skippy on the steps, because you have seen all the explanations of how to find the z sub c here back in the actual video lessons where I introduced the concept of finding inner confidence interval. So here, just first step here, it is going to be 0.5 plus half of our confidence level. So our confidence level in real-time decimal, 0.99, given in a problem. And so now I'm going to go 0.5 plus half of our confidence interval. Final calculation of mine showed 0.995. And this value right here, I call that, it's the left area. And so now moving on to step 2, I am going to use the program that I developed, or public viewers can also find a program over the web that serves the similar purpose right here. This program is going to take the left area that we have found and give out a z-score. And that z-score is now what we are looking for, the z sub c value. So finding z sub c is simply just a matter of running a program that takes this left area and produce the z-score and calculate out the z-score for us. So we're going to leave that completely for technology to handle. So my INV-Z program on the computer screen is here. So this time for the box right underneath the label left area, I am going to enter 0.995. And so the corresponding box where it's under the label Z right here is the z-score that the program that I have developed calculated for us. All right, and so now for anyone using a TI-83 or 84 calculator, the INVZ command is actually called INV norm in the TI-83 or 84 calculator. And to get there, we're going to hit the key combination second variables. And we look for INV norm. So once again, INV norm is the way how the calculator, the TI-83 or 84 calculator is calling the INVZ program. So now we're going to call INV norm by hitting enter. For a TI-83 user or any TI-84 early TI-84 user, after calling your INV norm program, you will be seeing the command line being printed directly on screen as following. And I will get back showing how we can complete this command right here. And so now allow me to proceed further with the current version of the TI-84 calculator that I'm using, where we are seeing a menu after calling the INV norm program. So for the area as the program is asking here, now we can enter 0.995. And that's all we need to enter. Anytime running the INV norm, we will default mu and sigma to 0 and 1. So now I'm going to just simply hit enter a few times to skip that, to skip the value, to skip those lines there. And then we're going to hit one more enter. So if you are on a TI-83 or early TI-84 calculator where your command, the INV norm command, is printed directly on screen, this is how you are going to complete the command right here by typing in manually the area, the left area value. So 0.995 is placed right after the opening parentheses, and with a comma, and then 0, 1 for mu and sigma here, and we close the parentheses. And now for all versions of the TI-83 or 84 calculator, we are going to hit the final enter. And this is our Z sub C, just like how we have seen that on the INVZ program that I wrote in Microsoft Excel. And so, unless being specified otherwise, usually my Z sub C, for all Z sub C throughout my lectures, I will be rounding to 3 decimal places. But it is viewers and students of mine's responsibility to find your own, to check for your own rounding requirements in any of the problem that you are finding Z sub C values. So here it's 2.576. And the calculation, as you have seen on the computer screen earlier, was a lot longer. But as I said, I'm only rounding this to 3 decimal places. And so now we really are ready for our final calculation of the margin of error. So the margin of error here, Z sub C, now can be substituted by 2.576. So 2.576. And that Z sub C value must be multiplied with the lengthy expression here inside the root expression. So 0.3778 in product with 1 minus 0.3778. And it will take a little bit of patience to do this entire calculation in the calculator. Plus 0.2222 multiply with 1 minus 0.2222 and dividing that by the other sample size N2, 450. And so now my final calculation for margin of error came out to be 0.0776. So the actual answer that came out from the calculator was a lot longer. But for this particular problem, I rounded down to 4 decimal places. And so it is viewers or my students' responsibilities to watch for rounding requirements for each of your problems that you're working with. But now, so in the margin of error that we're doing here, then now our final confidence interval is ready. So what it says now is that at 99% confidence level, or at 99% successful level, we found the difference dp is anywhere up and down by 0.0776, up and down from this sampling difference between the two sample proportions that we have had. So 0.0776 up and down from where 0.1556 was. So this was our sample value, and this is the margin of error. So this is our final confidence interval. And so at 99% successful level guaranteed here, then the actual dp will be somewhere inside of this interval. And then again, we can always add this margin of error to the center point here, and the same thing as subtract this margin of error to the center point right here to create a low end and high end. So low end, after we subtract 0.0776 from 0.1556 here, we came to 0.078 for low end and 0.2332 as our high end for this interval. And so the interval where it displays the complete low and high ends like this, we refer to this as the interval in traditional formats. And so I expect any of my students to be fluent with the two different ways of how we expressed our final confidence interval, either in the form of the center point up and down by the margin of error, or the interval that completely shows low and high, and we so-called the traditional format here. But once again, guarantee at 99% successful level over here, that difference dp is falling somewhere inside of this interval between the low and the high here. And so now that we have found our confidence interval that estimates dp according to the answer of question B we have just now answered. So our confidence interval to estimate dp in this case is the margin of error 0.0776, anywhere 0.0776 up and down from the sample value. Or in traditional format, we have found 0.078 and 0.2332 is the high in traditional format. Because it shows low and high. So from what we know at this point, our dp is, again, as a reminder, our dp is known to be inside of this estimate at 99% successful level. So how is this result in part B that we have just now found connected to the result that we have done in part A, where I put them all in one problem? So in part A, it was a testing of a hypothesis. So the null hypothesis was stating that dp equals 0. The difference in the two proportions equals 0. And we had strong evidence at the end of the test. We had strong evidence to reject that dp here could not equal 0. And indeed, we started to support, we leaned toward supporting H1, saying that dp should be higher than 0 or being a positive value. And so again, we came to this right tail test simply because of our starting labeling convention from the beginning. And so, but in this way that we were going, in that way that we have already decided for our process to test the hypothesis, then at the end of part A, the only thing we knew was that dp is highly believed to be above 0. But now, how far above 0? Being above 0 by, is that only by a small amount, 0.05, or being a larger amount, 0.5, or being an even larger amount like 1 or 2? We did not know that answer at the end of part A, because the only thing H1 was stating is that dp was above 0. And so now this is how useful the answer in part B is given. It gives a better picture of where dp should fall into. So now at the end of part B, after we're looking back at that, after we're looking at part B and connect that with part A right here, then we can see that now this interval is completely a positive interval, and so we now know a better picture that our dp falls somewhere inside of this interval. So it gives us a better picture from the result we have proven in part A. And now, before we're completely finished with this current lecture, and specifically the current example that I brought up along with the lecture here, then let me make a couple important remarks here. So back to the two populations that we have isolated out. So here we're studying the male drivers population and the female drivers population. And so now, if we roll back to that beginning point where we were deciding to give the numerical labels for each one of these populations, then if the labeling decision was the other way around, meaning it's population 2 for male drivers and population 1 for the female drivers, then these are the consequences that will be brought to all of the problems that we have done. Obviously, this population now is regarded as population 2, and this female driver's population will now be regarded as population 1 if we decided the labeling convention the other way around, as indicated here. And so that proportion of male drivers who favor driving a manual transmission would now be referred as a P2. And similarly, now that same proportion of female drivers who favor driving a manual transmission would be regarded as P1. And so now, and then when it would come to sampling information, then the sample size from this population would be similarly or correspondingly N2 to be listed as 450 in the sample. And so the sample proportion we found there from that population 2 is now regarded as P hat 2, where it was 170 over 450. So the information itself won't change. It's just we change the subscript and the actual numerical labeling convention. That's it. And the sample size from population 1 would now be regarded as N1, which was equal to 450 as well. And the sample proportion from population 1 now would be regarded as P hat 1, being 100 out of 450. And the numerical calculation would remain the same, 0.3778 here for P hat 2, but 0.2222 for P hat 1. And that was the reason why throughout all of my steps I keep mentioning that for whoever is playing in the role of P1 and whoever is playing in the role of P2, because here it's now different values the opposite value that's playing in the role of P hat 1, all due to that the fact that we have switched our labeling convention, and P hat 2 and the different decimal value is playing in the role of P hat 2 right there. And so, as a further impact for the entire work that we were doing, then the dp hat would consequently come out being negative 0.1556 instead of positive 0.1556 that we have seen back in the problem. Switching the labeling convention will not change our P hat C value, because the P hat C value simply just come out by totaling the two sample sizes. And I actually noticed a written error of mine from earlier. So sample size 450 from P hat 1 and sample size 450 again from P hat 2 and we go in 100 plus 170, and it would come out the same, being 270 over 900, which gives us a final piece of C, P hat C, 0.3. So as I said, switching the numerical labeling from the beginning here did not change our P hat C over here. But now when it comes to testing our hypothesis in part A, then the two hypotheses would look as following. Again, as a reminder, it's all due to the fact that we have permanently defined dP to equal P1 minus P2. And again, I have to say, for whoever is in the role of P1 and whoever else is in the role of P2. So in this case, P1 is actually the population proportion from female drivers, and P2 is the population proportion from the male drivers population. And so in that way, algebraically, as a consequence, the alternative hypothesis H1 would say dP is a difference that's less than 0. And you can spend some time doing a little bit of algebra to see the reason why, very similar to how I argued that earlier in our video lecture when it was the original problem. And that would make our problem a left tail test. And of course, the difference dP will equal to 0 as always. And so in that case right there, the problem would be proceeded as a left tail test, where at some point when we need to bring all of our sampling dP hats value on the bell curve, the approximate for sigma dP hats remains the same, and the center of this bell curve, representing the entire sampling distribution of all dP hat values, would remain the same, with center at 0. But now from this center here, our sample value, the dP hats we currently have, would appear to be somewhere to the left-hand side of the center on this bell curve. And so that means that consequently later on when we're calculating the area, it must be the area that's pointed to the left-hand side, because it's a left tail test. And so in that way it will make perfect sense that calculating the P value for our sample will be proceeded or set up as the probability that on this bell curve we're going to find a dP hat being this time less than or equal to our sample value, which was already known to be negative 0.1556. And so consequently, as the next step, this area here on our current bell curve will equal to the area on the standard normal distribution bell curve, where we're looking for a z-score falling below negative 5.08. Because now, so recall that this z-score here was positive sign when our labeling convention here was the other way around. But now since we switched the labeling convention, this z-score will consequently become negative as well, along the way with how our sample became negative. Then the remaining final step for the calculation would become the same, and the final calculation should once again become a 0, 0, 0, which exactly agrees with the answer we have found originally throughout the work that I've done earlier. But so now at the end of the test, in part A right here, if we had the labeling convention the other way around as indicated here and proceeded as a left tail test, then all we knew at the end of the test was that dP in this definition here must be a difference that falls below 0 or being a negative difference. So in that case, when we advanced over to part B of our problem, where we constructed the confidence interval, then the sample value that we need in the middle, in the center of our interval, is now a negative 0.1556. And from where that sample value is, we're going to be up and down by now changing the labeling the numerical labeling here will not change our margin of error, and we can easily algebraically verify that. And so the margin of error would stay the same, being 0.0776. But then now if we actually put this interval, this final confidence interval, in the traditional format, we will understand a little better about that. So the low end this time would become the negative 0.2332, and the high end here, by adding this margin of error to the sample point, which is now currently a negative due to that switched numerical labeling, then the high end would become a negative 0.078. And so now if you can see that if the labeling, the numerical labeling from the beginning was done the other way around, then the interval would turn out completely the opposite interval, where you can see that it's completely a negative interval, and it's in the end it's still consistent with the result we have proven in part A. So that's the remark I would like to make right there. So it's really important that once anyone doing these problems has decided a labeling convention, then make sure you stay in that convention, and this is the way how we keep things organized. And so for a testing hypothesis problem, in this way, to become a left tail or a right tail, it's all going to come out not because the statement in the question was saying less than or greater than, but because of how we decided the labeling convention here. And then from there, as you can, if you can follow your work carefully, then the result will come out and be consistent with each other. And now at the end of this lesson, I'm going to quickly summarize a couple of formulas that we have learned here. So what's new in this? The new formula we have learned here is that we approximate the sigma dp hat, assuming you already understand what sigma dp hat is. Sigma dp hat can always be approximate throughout all of these testing hypotheses for comparing two population proportions. Then sigma dp hat can be approximated by the p hat c times 1 minus p hat c, and multiply with 1 over n1 plus 1 over n2. And the entire lengthy expression here is to be put inside of a square root. So that's one formula to be highlighted that we used earlier, and it will always be the same formula to be used again anytime we're comparing two population proportions, and given that they are independent samples. And the p hat c that we used here, we're going to just simply take successive count that existed in sample 1 plus that successive count that came out from sample 2. We total up those two successive counts, and we divide it by the total of the two sample sizes, n1 plus n2. So this is another formula that we have learned throughout the work earlier in part A of our example, in continuation of the lecture. And at the end here, when it came down to estimating the actual dp, then the margin of error will be z sub c multiplied with the square root expression, where it has p hat 1 times 1 minus p hat 1 over sample size n1 plus p hat 2 times 1 minus p hat 2 inside of sample size n2, and all of that is again inside of the square root. And this is the formula to calculate the margin of error when we need to construct a confidence interval to estimate our dp. And as a reminder, so when we're looking back at the steps, if anyone can rewind this video to the earlier parts where I was showing the steps to find to calculate the z sub c. So z sub c is found the same way. In any other problems. z sub c. And what I mean here is that prior to this lecture over here, then we have seen other problems where we ask for confidence interval that require a z sub c calculation. So this way, how we're calculating z sub c now is done the same way of how it was done in earlier video lectures.